Yes. So, we have talked about what were these? Positional encodings, we have talked about word embeddings. We say we add them, but there is no specific reason why to add them. You could have also concatenated it, and I think, as I said in the last class, so this is probably at least to me one of the most, one of the hacks in this whole thing that I understand the least. Okay, that because the moment you add something, the moment you add something to input embeddings, you might actually perturb the word embeddings, right? But still this works, so this works. But as I said, later papers they have come, they have tried to change positional encodings. So in this paper they used fixed ones, okay? But later papers like GPT, what does GPT do? GPT basically learns these positional encoding, and there are other ways to find it too, and there are papers that say you just don't need this at all. Okay, so what is the exact status, that is not yet clear, so maybe we will have to wait more. But anyway, so we have done this, we have talked about multi-head attention. Now if you see, this add and norm is present in every small subnetwork here, right? So today we are going to talk about this add and norm. Okay, so and after that we will be left with just masked multi-head attention, which is a thing of 5 minutes. So we are going to talk about add and norm. Okay. So, how many of you have seen the videos? Awesome. Which video? ResNet, right. So, what happens in ResNets? So, right. So, see, in 2012 we had the AlexNet paper. Now, AlexNet paper started the modern deep learning. You can, so that explosion, whatever deep learning explosion we are seeing, right? A major reason is AlexNet paper, because that paper showed that you can use deep learning for such a large scale data set and it works really well. Okay. Soon after AlexNet, you had Word2Vec, right? So one was in vision side, another was in NLP side. So you have these two breakthroughs. Now what people in computer vision were doing, they were trying to classify images. So there is a data set called ImageNet dataset. It was created by Fei-Fei Li of Stanford. So this data set has 1.2 million images and 1000 classes. So the challenge that they had been holding since, I don't know, maybe 2008, 10 or whatever, the challenge was, given these 1.2 million photos, you have to classify each photo in their correct class. How many classes are there? 1000. AlexNet did this and their error was somewhere around 16%. And the second best was somewhere around 26%. So there was a big gap of 10% between first and second. And there was very little gap between third, fourth, second, third, fourth and so on. So deep learning worked really well there. So people started doing, so AlexNet paper had, if you count them in a way, 8 layers. So it was 8 layers deep. At that time you did not have TensorFlow, no PyTorch, nothing. So they wrote everything in C, used their normal GPUs, because GPU industry was not in boom until then. So it took them time, but they could finally show it. Then we know about the Word2Vec as well. Every year what people were doing was, AlexNet had this error of 16%. Then in 2013 few paper came that says ki error is now further lowered. In 2015, so what was common? So you had this AlexNet, and then I think VGG16 was from Google, VGG16, VGG19, so these are the number of layers, okay. And then we had GoogleNet, it has some other name as well, but this had, if I remember it right, somewhere around 22 layers. So essentially what people were doing was increasing the number of layers. And now this paper, this ResNet paper, so this was in 2015 by Hay et al. So this paper comes and says, I mean, this way if you keep on increasing the number of layers, does it mean your accuracy will keep on improving? No, right? So what happens? What do they show? They show something like this. What is on the x-axis? So this is your number of layers and this is your cost function. So ideally what should happen? I mean, ideally what do we expect? As you increase the number of layers, my accuracy, my cost function should decrease. But what happens in practice is this. So it starts increasing after hitting a sweet spot. Okay. So this paper tries to answer this question. Now that you cannot really keep on increasing the number of layers as much as you want. So there has to be some kind of, so now see, a very simple result in neural network, it states one hidden layer is sufficient for whichever function you want to learn. Now the number of neurons in that hidden layer might be exponentially many, but in theory a neural network with just one hidden layer is sufficient to simulate any function that you are looking for, okay, however complicated. But in practice we see one layer is not sufficient, people are using 8, 9, 22. So deep learning's theory as of now is not at all understood, okay. Now, so people try to do some hacks, one out of those 10, 20 hacks will work, and then we'll try to see what happened, why did it work. So this is what was happening, you increase the number of layers. So now they do it for, if I remember it right, what was the number of layers? They do it for 52, 152, I'm not sure if they did for 102 as well. Anybody remembers? Video talked about 152? Yes. So let us, I mean, it does not matter, these are huge numbers anyway. So if you start increasing this, what will happen? As the number of layers become 50 or 152 here, your cost function will start increasing again, and that is not something you had expected. So what and why this might be happening, can you tell me? What can cause this? And why is it so? Right, what more? There is one phrase. One phrase to explain it all. What is it? Vanishing gradients. Okay. What do vanishing gradients mean? You have so many layers, you will be back propagating. So if you have things like, you know, this is your first layer, this is your second layer, this is your 50th layer, and let's say my network is just 50 layer. So if I am doing classification, where will I compute the output? I won't be doing it at any of these. In fact, this is not at all a recurrent neural network, so I won't be doing it. In fact, GoogleNet does compute it at intermediate too. So you can do whatever with deep learning that you want. But assuming we are doing it in the last layer, okay? So we are computing y hat here, or I mean y here. Assuming we are computing y hat here. So how will you backprop? Y hat will be a function of all these matrices, but from what we know, it will be very difficult to see the impact of these guys in backpropagation, because right. So as you go forward, the impact of these gradients, so your J is here. So let me, J is here, and you know the impact of these guys will decrease. And why does it happen? I mean, we have done this before. This happens because of vanishing gradients, right? So what authors do in this case now is, what do they do quickly? Because then we go back to transformers. Right. So what authors do is, let me get rid of. So what authors do is, if this is by Lth layer, this is L plus 1, this is L plus 2. You short circuit it in this way. No, after linear, so not at the output, before you compute the output. So, right, tell me one more thing. Let's say our performance was best until layer 25th. Right? And the performance actually started degrading after that. My question is, why can't networks simply do this? That okay, if I've got best things here, then rest of my network does not learn anything. And all it does is learn identity mapping. If you keep it that way, you will stay here, because you have not changed whatever came after 25th layer. But because of the way these things happen, you know, even learning a identity function becomes difficult for the network. So it is not even able to learn the identity function, and it starts degrading the performance. Now the argument behind these, and they have been very, very successful. Initially I had no idea, I mean I did not want to do it in this course, but 10-15 minutes here and there does not matter. You take, doing this short circuit, what will it do? So you do it for every layers now. What will it do? It will give the, no, but what is the impact of it? Why should this solve the problem? So once you have these connections, these are called skip connections, you get back to this. You can remove L plus, no, the number of layers is still 52, 152. What you have done is you have added these, which part?
जो अपन लीनियर पार्ट में ऐड कर रहे हैं ना
राइट
शॉर्ट सर्किट
राइट
तो सर वो जो दूसरे वाली करती है L1 और
हम्म
L+1 और L+2 वाली
हम्म
तो उनके जो पैरामीटर्स है उनको तो आराम से वो लर्न कर पाएगा उनके साथ
see so help me write equations here now. So let me not write it this way, but this should have been no. So the output of this, actually this is what you sent. This is the right figure. Okay. Now tell me what is the output here? AL, this is Lth layer. So output of this layer is, let me write it here, AL. What are we doing here? AL you send, so what is the linear output here of L+2? Right. So this one, the output of Lth layer is AL. What is the linear output of L+2th layer? ZL+2. And what are we asking to do here? Add these two. So I should have directly written it here. No, plus AL. This makes sense. This is what we are doing. AL, we feed it to L+2. So when do we do this sum? Before we compute the non-linear output at layer L+1. Now this part, so this becomes, now what do we do? Now we take the non-linearity. G is my symbol for non-linearity, whatever it is, ReLU most of the cases. Okay. So this is your, what is this? This is what? Exactly. So this is A of L+2. This is what this short circuit is. Exact same thing is used in transformers as well. So, and this particular connection has been super useful. Everybody does it. So if you see here, this one you go ahead and do multi-head attention. What else you do? So before you take multi-head, what do? You short circuit it to here as well. Okay. Add means this add that we are talking about. Add, and then you take the layer normalization. What is layer normalization now? Is this part clear? We are doing very simple thing. We, whatever was here, we take that and send it to a couple of layers forward. That's it. Okay. So this is what we are doing there as well. Okay. As simple as this. Now, what is happening in, so this was the add part. Okay. This was the add part. Now we talk about the NOR. Did I ever talk about the difference between batch gradient descent, stochastic gradient descent and mini batch gradient descent with you guys? What is it? What happens in batch gradient descent? Then what is mini batch gradient descent? And what is stochastic gradient descent? So batch, see, that's why names in deep learnings, they are, not so good. Batch gradient descent is the one where you have full data set. Okay? So you compute all, so, I mean, what do I mean by batch gradient descent? What am I going to do with this whole batch? Right. So coming back to those 4 lines of my training, what were they? Until convergence, compute J, compute grad J, and then update W equal to W minus alpha grad J. Okay, and similarly for B equal to B minus alpha grad J. Now, in this, when you update, so the difference between these 3 is, in batch gradient descent, how often do you update? You compute J for the whole data set, whole training set, and then you compute gradient of J, and then you update for that. So let's say if you have 1 million examples, what will you do first? You will compute J for all these guys, right? Then finally compute whatever J, because J is going to be the sum of all these losses. So that becomes your J, then you compute grad J, then you update. What is wrong with this? And why is this expensive? Because you will do this anyway. See, if you are running training for 10 epochs, that means how many times you are going to look at the data? 10 times over same data. Does it matter you are doing this in mini batch or whatever way? You are going to look at data size cross 10. So you are going to pass this many examples through your network. So why do mini batch and not batch? There are good properties with batch. What are they? So this is, yes? So why? See, when you compute J for this whole big data set of 1 million images, this is going to take you time. Let's say in your code, instead of writing W equal to W minus alpha grad J, you wrote W equal to W plus alpha grad J. Mistake. Okay. And now you throw your training, sleep, you wake up in the morning and you realize there was this bug. Okay. So on these big data sets, if you do batch gradient descent, it will take a lot of time to give you the first update. Okay. Whereas if you start doing it on a small batches, you will get the behavior of that function that we draw. See, in case of batch gradient descent, you start from here, and to reach here, that is in the first iteration, first epoch itself, you will take a lot of time. Whereas in other things like mini batch gradient descent, what will happen? You will update it for a small batch, let's say of size 512, right? So you could see much more updates, you could see where are things going on. If you see that things are going this way, you abort the training at that moment itself, see what is wrong. Okay. So this coming from batch gradient descent to mini batch gradient descent, one of the big reasons is training, I mean the first update, right? That is probably the biggest reason why would you like to do this, even though there are mathematical reasons too. Now what is stochastic gradient descent? Just one example. And in deep learning, see, what you train on is not what mathematicians study. So those who are studying these optimization methods, so what is stochastic gradient descent? One example. You update on every example. Okay. Now, every example update is going to cause a lot of noise. Why? One example will be good, so your loss will be small, but next example might be a very bad example. Your network did not do well, so the loss increases and this keeps on happening. Eventually that will also decrease. So the average of those things, you know, this is like stochastic gradient should behave. Eventually that should also decrease like this. Now, the question that we are asking here in case of norm is, okay, so in norm what we are saying, so we know deep learning hacks. Who told you to use ReLU here? Why should we use ReLU? Earlier you were using sigmoid, then you started using 10H sometimes, and then we say we'll use ReLU, then somebody comes says we'll use leaky ReLU, then somebody says we'll use GALU and so on. So, because we don't know what is the best thing, okay, we don't know it yet. Now, so what is happening here? What are all these layers computing? Whatever they compute, you pass it to the next one, you multiply with the weight matrices, you do the, you add the biases, you take nonlinearity again. Whatever nonlinearity you take, it is going to throw some values. Okay. Now, what normalization does, and what I have completely skipped here, I don't think I have talked with you guys about batch normalization. No, right? So, some numbers will be thrown out here, okay, at every layer. What normalization says is, you do things in a manner, so this is my layer, so this is my current layer. This will compute nonlinearity, I mean at the end it will apply some nonlinearity and will give you some outputs, right? What normalization asks you to do is make every output in some sense coherent. Let me try to explain this more. So, for one example, can the output of these two things differ very much? Let's say you are doing that same classification problem, image classification. Let's say there is an image of dog, your network comes and say there is dog in this. Okay, so you will output something. So right now you are going right, network is trying to do the right thing. Another image of dog, but let's say your network for whatever reasons is going to say no. So can I expect that these two images will change my weights differently? See, in the end, what changes weight? So we are now considering, we are passing example by example. What changes my weight? What is it that triggers my weight change? Error, right? So you will have loss at the end, you will backpropagate that loss and you will tell each and every weight you should change by this much. You did that change? So let's say you did in the first one. Second time some image comes, what will you do now? Change according to that image, right? Now, can these numbers, the output of these guys, can they vary significantly? See, what I am trying to say here is, these weights, you change them every example. Okay, let me speak minimum. Every example has potential to change these weights. You are passing example by example, and that means you will update in every example. So every example has potential to change these weights, right? Question here is, you want to keep this coherent. What does it mean? See, this guy is computing some non-linearity. So this guy is computing some non-linearity, this whole thing. We don't even know which non-linearity works best. So if you are using ReLU here, is it different? So these values will be different if you use sigmoid. These values will be different if you use leaky ReLU. These values will be different if you use some other thing. So as such, these outputs, there was nothing special when you were using ReLU or GeLU or whatever, right? These outputs may change. So what authors of paper called layered normalization come and say, they say we want to keep it coherent. So in the sense that this is my Lth layer and mu L will be 1 by H summation I equal to 1 to H. So again notation comes here. What is H? H is the number of units. Okay. So H A L I. What is this number? What is this number? I goes from 1 to H. So what is this whole thing? You are summing up. So basically summation is over everything. You sum all these values. Then you take 1 by H. What is that? Average. So mu L is the average at this one. Okay. What is the other thing that we compute? What is this guy? What is this guy? Variance, right? So this is our variance, mean variance. So what layered normalization comes and tell you, whatever value these neurons are outputting, in the end you should make it such that their mean is this and their variance is this. So their mean is fixed, their variance is fixed. What impact will this have? See, you should also go and watch the other LLM course from IIT Madras. Okay, I sent you the link because he explains it differently. I am trying to be a bit different from what he explains so that you take union of both. Yes. Mu L sigma. So what we are saying in this case? See, think of it this way. that these units will be computing some numbers anyway, and since I can always go and change non-linearity, there is nothing special about, so you can't come and say, why did you, why did you change the values that were coming after taking ReLU? This will change those values. See, if you are forcing that mu should be this and variance should be this for all my examples coming, are you changing the values that come after nonlinearity? Yes, you are changing. Okay. So you can come and say, why change them? But the point here is, you don't even know which nonlinearity works best. So there is nothing sacred about these values that are being output. And the moment you took these layer normalization, it helps you converge faster. So your weights are learned in a manner that helps the gradient descent converge faster. Yes, this is layer. It is giving me some values. These are my values. I normalize them. I normalize them such that these values will have mean equal to this. So I have these values. I have my first value A, L, 1, A, L, 2, A, L, H. These values are coming. Okay. What will layer normalization do? Layer normalization will say, go ahead, whatever these values are, they can be whatever, but their mean should be this mu L. Okay. So no matter how many examples you are passing through this network now, what will be their mean at Lth layer? Mu L. Right. So what problem does it solve? Without layered normalization, your earlier numbers could be very different. Now you are trying to confine them in some zone. What is that zone? See, if some good example comes, let's say these numbers were whatever, some bad example comes, the mean will be very different from what it was earlier. I need questions. These guys? See, no, we are keeping the mean same. So what is the mean of minus 10, 0, plus 10? What is the mean of minus 8, 0, plus 8? What is the mean of minus 2, plus 1, plus 1? 0, right? So let's say if these three were my outputs here, they are all valid outputs in this case because their mean is 0. So assuming my mu L was 0. But if you don't like 0, take average 10. So values are 20. Huh? No, see. Yes. These values could be whatever before I do layer normalization. Yes. So these values could be whatever. Now for some example, you are passing all these examples through this network. So for one example, let's say value of these is something. Eventually they will go and give me a different loss on this example. Then I pass through a different example that will give me a loss. let's say these losses are very different, okay, and they end up both changing these W's in a very different manner. One will send them to the negative side, another will send them to the positive side. What will end up happening in your training? In the end, what do you want to converge? In the end, you want to converge W's, but what my last two examples have done? One decrease the weight, another one increase the weight, and you keep on doing this. Do you see the fluctuation that we are going to do through every example? What are we trying to do through layer normalization? You reduce this fluctuation. It's not that you are making it zero, right? You reduce this fluctuation because now we are imposing a thing that however good, however bad an example is, these output that it is going to output will have mean equal to 0 or mean equal to mu L and variance equal to sigma L. ट्रांसफॉर्मर पे मत जाओ, पहले इसी पे बात कर लेते हैं अपन. हाँ, we are doing it for every layer. How I compute my AL is immaterial. So before AL, you have computed a linear part called Z1L. Exactly. See, ZL is my linear part. You take some non-linearity, get this part. So computation until here, there is no layer normalization right now. After layer normalization, what will be the difference? These numbers, they can't be just arbitrary whatever. They have to just respect these two criteria. Their mean must be mu L and their variance must be sigma L. They can be whatever, but they just have to respect this. We are not doing that. If you use sigmoid, these ALs will be different. If you use ReLU, these ALs will be different, AIs. If you use GeLU, they will be different. If you use 10H, they will be different. So if they will be different, if you have got so many candidates to compute nonlinearity, what I am coming here to say is the absolute values of these A's, it does not really matter that much. Because one day you come and say ReLU works fine, another day you come and say GeLU works better, and so on. So there is nothing super secret or super sacred about these numbers that you are getting here. Now, what was that weight update thing? See, what is the impact of these guys on my weight update? See, forget this. For a second, forget this. Okay? You compute Z, you compute A, and if you don't put any restriction, you keep on doing this. Okay? These guys are unbounded, they can take whatever value they want, right? So done. When the moment we say they can take whatever value we want, now what do gradients here depend on? These gradients depend on what? These gradients here, they depend on what? they depend on Z2. So basically, if you remember, when you will compute the gradients here, they will be a function of the layer preceding them and the layer succeeding them. So both the sides of layers, because you will have del terms, you have this chain rule, right? So this guy will have terms from here and terms from there. All we are saying in this case, so you do this Z1A, this ZAL computation at every layer. Keep on doing the way you were doing before. All we are saying is, you compute ALs after layer normalization such that your mean of these values is mu L and variance is sigma L.
सर वो नॉर्मलाइजेशन कर क्या करें? नहीं सर, आपने बोला कि नॉर्मलाइज करने के बाद अपन म्यू एल कैलकुलेट करते हैं.
So it's a standard thing to say my mu L is 0 and this is 1.
इनका कुछ एक्चुअल मीन और वेरिएंस भी तो आएगा ना, जो ये A1 A2,
Exactly.
तो वो कैसे बनाएंगे म्यूएल और सिग्मा?
So see, these values you are forcing that their mean should be, let's say, 0. So if you are forcing it, they will sum to 0, right?
इन दैट ए को अपने को अपनी मर्जी से मैनिपुलेट करना पड़ेगा. A1 A2.
Yes, so A1 A2 will, after using layer normalization, A1 A2s will change such that they respect this. So they can't go unbounded, whatever they wanted to do, that freedom is not there anymore. So all your examples that you pass through this network, the moment they start respecting this structure, it can't happen that one update takes you somewhere and another takes you radically at a different place. I'll take more questions here.
तो मतलब सर अपन इटरेटिव प्रोसेस कर रहे हैं यू और इसका क्या सही मतलब मीन और वेरिएंस का.
Where is iteration coming from?
अगर अपने को उसको सही बनाना है अपने हिसाब से,
There is no सही और गलत.
मतलब मीन अपने को सेम रखना है.
What we want to do is, see, just this. Earlier these ALs could be anything. Now I am imposing a structure on them that their mean should be mu L.
तो सर वो कैसे करेंगे? एल चेंज कैसे होगा? अपन रैंडमली तो चेंज नहीं करेंगे.
I don't get this now. What is the question?
सर जैसे A1 और A2 कुछ और आ रहा है और मीन के हिसाब से हमें ये रखना चाहिए, तो वो चेंज कैसे होगा?
No, if you are putting this one extra equation in your layers here, then all this guy wants is this summation should be mu L. That's it.
तो सर म्यू एल आ गया. फिर उसके बाद क्या करेंगे? मतलब अभी तो एक ड्रीमिंग एग्जांपल है. अगले पे जाएंगे तो अगले में म्यू एल कुछ और आएगा.
You can take mu L. So mu L plus 1 could be something else, but usually you will keep it 0, let's say.
तो सर वो मतलब
अगर वो जीरो नहीं है सारे,
There cannot be a case of it won't be 0 because you are enforcing this at every layer. So every layer, once it will compute A's, it is supposed to compute A's such that their average is mu L. कोई क्या चीज? Mu L is something that you decide what will be mu L. Usually it is kept 0 and 1.
सर फिर एएल जब अपन वापस से इवैल्यूएट करेंगे क्या आना चाहिए तो सर वो किस बेसिस पे होगा? मतलब कुछ तो ऐसे रैंडमली तो डिसाइड करेंगे नहीं कि A1 ये हो जाएगा A2 ये हो जाएगा.
Okay. What you were doing earlier?
सर z अपन ने ये कैलकुलेट किया आगे चलो.
So there was no structure at all. Now you have just imposed this structure that these ALs can't be any arbitrary number, they must have average mu L. That's it. Earlier it could happen that if if my first example comes, average is 0, second example comes, average is 10, third example comes, average is minus 20. Now you are saying no. So earlier your A's could be anything. Right now we are saying they can still be anything, but their mean must be mu L.
सर जो वेट्स अपडेट हो गए L1 और ये वाली इसके बाद तो वो भी तो सारी लेयर्स के प्रोपोर्शंस में ही आएगा
Weights, yes.
हाँ वेट्स जो अपडेट हो गए मतलब अगर इसके वेरिएंस के अकॉर्डिंग इसके वेट्स
No, so let's say now, let's say average of these guys was, let's say average of these guys was 10 in one example, and it becomes minus 10 in some other example. Do you think they will change these weights drastically compared to if both of these examples have mean equal to 0 here?